record it. So Lina will help us record the webinar. Lina, will you please do so? Oh, I see already. You did already. Okay. And we will be able to share a link with you after the webinar. So we welcome you to revisit the content and also share the content with other colleagues who could not join today. And also for best experience, please keep yourself muted unless your name is called. And of course, we invite your comments and questions. So please look at the chat box on your screen. If you think of a question for Professor Debbah at any time, just type the question in the chat box, and we will get to your question during the Q&A session at the end of the presentation. So next, I will introduce the speaker, Professor Debbah. In my opinion, he does not need an introduction. He's one of the most well-known figures in our community. So he's now a professor at Khalifa University, and he's the founding director of the Khalifa University 6G Research Center. During his career, he has received so many distinctions, prizes, and best paper awards. So at this time, I'm going to hand the floor over to Professor Debbah, who is going to start today's presentation. So Professor Debbah, it's all yours.
Thank you. Do you see my slides, just to be sure? Yeah?
Yes, I can see it.
Okay, so very, very good. So first of all, thanks for having so many people to listen to the kind of message I want to push with the work that we're doing since a couple of years on the interface of what we call here LLM and telecommunication, which I think is a turning point today within the domain of telecommunication, where we're seeing, of course, as all you know, what we call convergence of communication and computing within, of course, the telecommunication market. I think this is also a great opportunity also for all the people who have been doubting about basically the future of telecom, in the sense that you all know the sector has been going through a phase of crisis these, I would say, last 10 years. Roughly because, of course, we were considered as dumb pipes, in the sense of dumb pipes, meaning that we just transport all the data. And the kind of revenue that was being generated by that was going down each year. I think today we have a great opportunity to revamp basically the telecommunication sector because we are at the moment basically the infrastructure, and that's what I'm going to push as a message, where ubiquitous intelligence will be running. And ubiquitous intelligence will be running in a very distributed way in the future. And I think that also will come up with a lot of new, I would say, opportunities to monetize basically the business on which we're working as of today. And so, of course, the talk is not going to be talking about the business aspects, but I think many of you who are working as operators, which are working also as telecommunication providers, I think the time today is a good time for you to start thinking about the business opportunities that you can leverage basically from the technology that we're building with respect to basically this convergence of communication and computing. As far as I'm concerned, I've been working at an interface basically of telecommunication and AI for a couple of years. Of course, started my career like many of you within the interface of signal processing, information theory, telecommunication, and also what is a very specific feature of my career has been I've been moving from industry and academia back and forth every time. And so I think this is also very important aspect, I think, for research. I think it's very important when you develop basically some kind of technology to see it basically, of course, coming into production and that coming back again to basically the work that you're doing. And I'm quite confident that this circle of, let's say, creating knowledge at academia and making knowledge converted into, I would say, business or money is a very important step in the terms of cycle, how things should go on with respect to what we do. Now let's go to the purpose of my talk. The talk, of course, goes within a series of talks that we'll be organizing. And I'll talk about it at the end, which are what we call these emerging technology initiatives, which basically one of the emerging technology initiatives that we've been pushing is around generative AI. And of course, I'm kicking
Professor, you are on mute.
Oh, sorry, I don't know. Yeah, work in this domain is always, of course, supported by people you work with. Things never come alone, and for that, of course, I'd like to thank many of my co-authors, and I'll be putting a couple of papers in these two slides to show that a lot of this work has been what we call collective work, meaning that I've been working with outstanding people, either at the telecommunication front or the large language model front. You have here a series of papers, which are, I would say, the basis, if you want to go deeper at my talk, which have been published quite recently in terms of the interface of, I would say, LLMs and telecom, and trying to understand what we're talking about when we're talking about large language models for telecom. And many of the people here belong to different institutions, going, of course, from Khalifa University to the Technology Innovation Institute, but also colleagues that I have been working quite strongly, also like Walid Saad from Virginia Tech, people like Christina Shakur, also Christo, and also Zuhan, and also Omar, working mostly on semantic. And I'll talk also about why semantic is also part of the things that we're talking here today, if people have no clue. Now, let's go around basically the initial, I would say, step by step in terms of understanding. I think all of you are familiar with what we call the G waves, and I think we've been going from generation to generation on, I would say, 10 years time frame, meaning every 10 years there's a new generation coming, which is mostly defined basically by some kind of use case, and behind, of course, we have KPIs. In general, it's one use case, but we've seen quite recently many use cases which were defined. But roughly things in the digital domain have started with 2G, which was mostly tailored for mobile for voice. Behind, of course, this kind of KPI, there is, of course, lots of technologies which fulfill that. And just to give you an example, from mobile for voice, as you all know, one of the key technologies is GSM, but GSM is not the only one or the only technology which fulfills basically mobility for voice. You have also IS-95 and others. 10 years later, we have something called mobile for data. And I think you're all familiar with these dongles that were being pushed, mostly to provide data, basically, in a mobility setting. Around 10 years after, 2010, we started providing what we call mobile for internet, roughly an ADSL or wireless ADSL experience with mobility, meaning the same thing that you have at home while walking outside. It's quite nice to understand that basically, of course, every time these technologies evolve, and we're not, I mean, they don't during 10 years, you have some evolutions. And for the case of mobile for internet, I think it was very important to notice that we are so focused in building basically an infrastructure called 4G that provides mobile for internet, that voice was not working well when we deployed the first smartphones. And one of the reasons is that, of course, in 4G, voice is an application, not a technology. So it turned out, for some people who are very familiar with the topic, that we used to have something called CS fallback, circuit switch fallback, meaning that whenever you made a call on a 4G network, you had to switch to a 2G or a 3G network. And whenever you browse on the internet, you stayed on 4G. And why I'm talking about this case is that that case was a lot of work that during the years 2014, 2016, I had to do, in the sense that I was requested to work a lot on improving what we call voice over IP in 4G systems. And of course, one of the things that happened is that AI turned out to be a very good tool in enhancing basically what we call AI-based voice over LTE. By the way, in 4G, there are various technologies which fulfill the 4G criteria. WiMAX, I think some of you may be familiar with that, but we have also something called LTE. And so trying to improve voice, which is an end-to-end metric in the sense that when you look at voice in an IP setting, you have a lot of protocols which get in. And so you can model very well, basically, the SNR, the signal-to-noise ratio, for people who are not familiar with that. But it turns out that even if you have a very good SNR, meaning the number of bars that you have in your phone, it's not necessarily the case that you're going to have a very good voice, because behind you have, of course, a protocol with IPsec security and stuff like that, which hinders, and we're not able to model this effect. And using AI techniques already around 2015, 2016 turned out to be quite useful in trying to optimize an end-to-end metric in here in this case. 2010, 10 years later, we had what we're doing now called mobile for things, meaning mostly IoT. Surprisingly, although it's not very surprising, the majority of network that we're building at the moment and deploying do not provide basically the two features, which is what we call the massive machine type communication and what we call the ultra reliable low latency communication, but mostly have been focusing on the MBB. And one of the reasons is that we still don't have a way to monetize basically IoT. There's still a question of business cases that are not clear. And I think starting next year, I think we'll get around that and we'll be starting to know better how we can monetize that. And now what we're targeting is something around 2030, 10 years later. Of course, the technologies have to be built right now. We'll talk about them. And one of the things that people are realizing is that AI LLM feature as of today, but there's no reason that LLMs will be continuing like that, will be at the heart basically of how the system will communicate. What I mean by that, what we're seeing is more and more what we call basically an AI at one point wanting to communicate to an AI to another point. For as an example, a chat GPT talking to a model called Falcon or whatever, Claude, for example. And so the question is that if you start having AIs discussing together, what are the protocols that you need to build which make the system of communication quite efficient? And let me give you a couple of examples that showcases you that you have to think differently. First of all, basically, today, the way you are doing basically a data transmission, in general, you have data at one point, you try to compress it through an algorithm of compression, and then you transmit it basically, and then you decompress it, call it JPEG, whatever. Now, if you have a model on one side, another model on the other side, and if we look at the LLM feature, for example, LLM are super compressors. So what you could do something like video to text. And then what you decide to transmit on the other side is not anymore basically the compressed data of the video, but just basically the instruction. Okay, just the text. And the other side, you do text to video. Now, if you do that, there's two caveats. The first one is you need to build a system. So this is like a super compressor because you're able basically to recover all the video just by the prompt that you write. Now, if you do that, you need a system that guarantees an end-to-end latency, which is quite small because the kind of mobile edge generation, and some of you, I think, had the capability of using that, will take a bit of time. So if you want to have a system in which you have a latency which is guaranteed, you need to build a RISE protocol on how you do that. Second, and some of you, I think, have been using this model, if you prompt the machine once, you get a result. But if you prompt it a second time, a couple of hours later, you don't necessarily get the same text. Okay, and so in this sense, basically in the communication, you won't get the same video. But if you realize how we humans communicate, we're in the same way. If I ask you a question right now, you'll answer me and give me an answer with a certain basically phrasing. If I ask you the same question in 2 hours, you will give me the same answer, but not the same phrasing. But we are still able to communicate, and what counts is, of course, the understanding I have of basically the instruction you gave me. And so we see that there's also a change of how we define communication, where we're not looking at perfect reconstruction, but we're trying to redefine the way of having something where there's a common understanding between the two devices that we have been building and where the meaning has been transmitted in some sense. Of course, this has opened the door to a lot of research at the moment of many people looking at things like semantic communication and other aspects. Second thing also that we're realizing is that the way we're building the telecom structure is the fact that we don't need basically anymore what we call apps. Okay, what I mean today, whenever you want to book a car, you want to go somewhere, you have on your iPhone or any kind of phone a couple of apps. You go on Uber and then you do all the things, transactions, and you go. Today, we're seeing what we call app-free phones, which are converted by agents, meaning you just have an interface and you just say, I want to have a car in 5 minutes below my house. You will have what we call a large action model, and you'll have basically agents which are interacting. So you need to build infrastructure so that these agents basically can work within an environment where basically the notion of app will disappear, and where these agents, of course, will be working at the speed that we need, with the reliability that we need within such a system. Now, you can ask me a question, and I'm sorry to spend so much time on the first slide. You can ask me a question is, why wouldn't be able to do that on a 4G, basically, kind of, 5G, sorry, kind of infrastructure? Well, this is reminiscent of many questions that have been in the past. I recall many people telling me that 5G, that massive MIMO is a 5G basically technology. Massive MIMO has nothing to do with 5G. You can build it for 4G, you can build it for 3G, you can build it for 2G. However, if you decide to implement massive MIMO in a 4G standard, you will realize quite rapidly that the kind of frame structure that has been built in 4G limits you on the number of antennas that you can go on a massive MIMO setting. In fact, many people, and I worked on that, you are limited basically by the kind of channel estimation signaling that you can do, and the maximum you can go is mostly 24 antennas, dual polarized. And so the development of the new radio that we have built, of course, opened the door to go more into basically exploiting the full capability of massive MIMO that you get in something similar to your MATLAB simulation, which enables you to get that degree. Same thing for people who today working on a technology called lease and reese. Many people tell me that lease and reese are just 6G technology. You can do lease and reese in Wi-Fi. You can do lease and reese for basically 4G. You can do lease and reese within 5G. However, if you decide to implement lease and reese within these standards, you will realize quite rapidly that there's a limitation because of the fact of the framing of basically on how these frame structure were made in terms of the signaling format. And you cannot exploit the full potential that you will get theoretically in your simulation, either through MATLAB simulation or realistically. And so you need to think then on how to build a new standard, which basically with the interfaces, which enables you to go up. And here we're at the same setting. You can always build basically a semantic type of system within a 5G system. But then you have to ask yourself, within the latency and all the things that we built, are we able to push to the limit that we have of going much further? And I think these are important questions that whenever we invent the technology, we need first to think on how it can be applied to the actual standard, what's limiting us in the actual standard in terms of the structure and frames that we have, what we need to take off from the actual standard to build a new standard so we can, of course, free the degrees of freedom to exploit what you're having when you're not limited in standard. And something important, of course, that also is happening today, and I'm talking, sorry, it's not around 2020, but it's around 2030, is that there's also for us, within the realm on which we're working on this convergence that I'm talking, something that is going to happen around 2030. And two things are going to happen around 2030 that we need to exploit quite efficiently. The first one, of course, is the realm of the progress that people are seeing around what we call the superintelligence. I give you a graph here, which is extracted from a book or paper, you could call it, called Situational Awareness, which is well written about thinking about how the things are evolving and where we're seeing basically a big bump in terms of how AI is going to happen. On our side, on 6G, we're also working, as all you know, on the fact that we want to build basically the standard to be released by 2030. And so this convergence of both systems of this AI, which is becoming more and more powerful, and basically the fact that 6G with its capability, we'll talk about it, is happening. A lot of people are seeing, of course, the fact that 6G is becoming the gateway of AGI. Why? Because a lot of the AI protocols that we've built today are basically not mixing what we call the digital world and the real world. What I mean by that, and I think some of you are familiar with LLM will learn mostly on text. And it's not basically interacting with the environment through sensing capability. 6G, of course, has a big component related to 6G, to sensing and communication. And of course, embedding basically this or grounding these models to reality will make a big bump. And this grounding of reality can only be made by basically the kind of capability that 6G is providing in terms of what we call 3D image reconstruction of your environment and how you're starting to interact and incorporate through sensing mechanisms. We have a nice paper which has been written by with my colleagues, which of course looks at those aspects about what is missing basically today in AI and how 6G can be the last basically component to bring what we're saying. So that was for a general introduction in terms of motivating you on the way we go. Now, let me go on the core of my talk. If you never heard about basically large language model and never heard about 6G and what we're doing right now. I think 2023 was a major date. It was a major date because basically it was the kickstart basically of what I call here the generative AI race. We had in 2023 and also this year a plethora of models being released one after the other, each one within a certain ranking. These rankings, of course, are based on evaluation benchmarks like MMLU and others. and also some which were open source and closed source. We won't talk about the closed and open source, but this has been effectively the year where things have been kickstarting of understanding basically the power of generative AI. Within, of course, the UAE, we have been also working quite intensively in building these models, and I'll talk about it. And one of the most known model that has been built in the open source domain is called Falcon, where in 2023, we released basically a version of a model with 180 billion parameters, basically top ranked at that time. And now we have a couple of new versions on which I'm going to talk about. Now, I'm going to give you a crash course on these LLMs, which I think is quite important to understand. and how they work, because and how then we can use them. Of course, in general, people think that the more your model is big, the better it is. And there's been, until I would say roughly 2022, a race of people trying to build models which were bigger and bigger and bigger, which were not things that for us in telecom is good, because if they get bigger and bigger, then what it means that you can only cloudify them and only access them through a cloud, because you cannot run them. However, a nice paper appeared that I strongly encourage you, called Extreme Scale Language Models by Kaplan and al. And that paper had also an impact on the telecommunication industry, of course, on the LLM. It was saying basically that when you build models, size is not the only thing which matters. And this is quite important, because if we want to port AI for LLMs on the edge, we need basically models which are quite small to build. And in fact, you can build small models, but basically you have to play on two other criteria. The first one is the data size and the quality of your data. And so if you have things which are of things like 1 trillion tokens, and going up today to 15 trillion tokens, then you can build a Llama 3B, very good, with 3 billion parameters only, instead of going to, as you can see here, in 2003, something like Megatron, 530 billion parameters. The second thing also is the number of epochs, how many times you compute. So the longer you compute your model and you do rerun, the better it is. Of course, there's always a plateau, but already if you do it a couple of times, you can have a model. So what it meant somehow is that we're able to build smaller models, which are extremely efficient, up to what I was calling here the 180B, which could have good performance if we could play on these other two basically type of sizes. For people who have really no understanding of what I'm saying, well, it's like if you want to train a kid. If you have a kid and you want to make him smart, well, first he has to have a certain number of neurons in his head. So the more neurons are developed, which is like 8 years old rather than 3 years old, then of course is going to be a bit smarter. It depends how you define smart. Second is, of course, the number of books and basically the quality of the books. If you give him random books, it's not going to be the same as the good choice of books and a lot of good books that you do. And the third one, of course, is basically how many times he reads those books. If he reads them one, it's not the same that if he continues rereading and relearning and going on with that. And if you play with these three things, then you can have something extremely powerful. And of course, for us, it's important because it means that we can pour these models within our infrastructure, and which is the edge infrastructure that we're talking. When I'm talking about edge, base station is edge also for me. Okay. And of course, basically, you have to know that beside those scaling laws, submodels already appeared, and we took a lot of advantage when we built the Falcon around that. A lot of models, some models started to appear, which exploited those scaling laws. One of the models which first they tried to exploit that, I mean, as far as I know, but maybe some of you would point to some others. One of the models which made a lot of hype at that time was a model called Chinchilla, which had basically only 70 billion parameters, which is quite high, but compared to Gopher, which has 280 parameters, was outperforming basically Gopher with only more data that you had. And so, of course, within the UE, this had convinced us that we could start working on building models with much smaller sizes by playing with their basically data. And we built a series of model called the Falcon series of open language. We have a paper that you can read where we detail nearly everything with the 3 series of model, one called the Falcon 7B, the Falcon 40B, the Falcon 180B. all open source, trained on various, as you can see, sizes of GPUs, going basically from basically 384 A100 to 4008 And these models in 2023 were top ranked #1. We continued the series of open source model by releasing the Falcon 2 series, with having also in these models what we call multimodality. Multimodality meaning vision. And we'll talk about that because in telecom, language is not the modality we use in general. We have, of course, RF signals. We have other things that we need to exploit to improve basically the performance when you want to build up something familiar or similar to what we call a telecom GPT. Today, the Falcon basically 2 is an 11B model. And of course, it runs on one GPU. And that was one of the purpose that we wanted to push, is to make sure that we could run these basically things more on the side so that people could exploit it with that. Now, if you never heard and don't know how LLMs work, I'm going to do also a couple of slides just to tell you a bit of the story around that. I think you're all familiar with what we call natural language processing. And until 2017, the people who were working in NLP were mostly using basically what we call bag of words. And the bag of words was mostly about clustering basically your things in something called Word2Vec. So you would put a woman as a queen, a man as a king. And this is based on, of course, statistical rules or correlation based, where you look at similarities on how things are happening. Now, for people working in NLP, well, these techniques had some caveats that people have tried, of course, to improve. And they were based on something called sequence-to-sequence modeling with some architectures such as RNN, LSTM, and GRU. The kind of drawbacks that these techniques have compared to what we have today when you want a scaling is that first, they were sequential. And of course, it's not parallelizable. And in general, in every invention that you do, if you have an invention or an idea that does not scale, in general, it's not a good idea. You need to find a way to scale it. By the way, it doesn't mean that you cannot make RNN and LSTM and GRU scale. I'm sure maybe some people will come with that within the field of something like space state models or whatever. But at that time, in any case, it was not parallelizable and you could not scale. And that was a bit of caveat when you wanted to crash a lot of data because it takes time. The second thing also, it failed in learning long dependencies, okay, and failed in long sentences. And if you had the experience of using basically the systems if you were experiencing using the systems of generative AI, you have realized quite rapidly that basically you use a long text to go inside. And so in 2017, a nice paper appeared called "Attention is All You Need." And by the way, now there's many titles of conferences, talks where people use the word intention in it. Attention is all you need. Computing is all you need. Whatever is all you need. In any case, this paper was authored by researchers from Google Brain, Google Research, and University of Toronto, and they came up with an architecture which solved the two caveats that I was talking about: the fact that you needed the parallelizable architecture, and that it can learn long dependencies, and that's what we call the transformer architecture. If you have one time to read, if you take the opportunity to read it, you have to know that it's not a simple paper to read, at least for me. It took me a couple of loops to read it many times to start understanding what they were doing. It's not a very easy, from my point of view, paper. However, each one of the authors today, I didn't take a look at it right now, I think has a citation index of something like 200,000. So with only one paper, each one of these guys basically has a higher citation than any academic researcher I know at this stage. So it tells you, of course, the importance of that paper. And so what exactly that paper was trying to do, and what are we talking when we talk about basically modeling a language? Well, basically, it's only a question of how you basically model what we call conditional probability distribution. I'll give you here a sentence called: the capital of the United Arab Emirates is Abu. And the goal is to find what is the probability that X is equal to Dhabi, knowing that the capital of the United Arab Emirates is Abu. And so finding that is not easy because you need to model that P of X. If you model that P of X, then you can find all the different X's which are possible. And then you put the most likely, and you're able to predict the next word. Once you predicted the next word, no problem. You can based on your prediction, predict the next word and do the same thing as a routine. And you can generate a full text. And this is how these basically what we call autoregressive type of systems work. So in a sense, it's quite easy when you think about it, because we're building a probabilistic system where each time we're trying to predict the next word by just giving the most likely. Now, finding the P of X is not easy in general, because you need to model. And when you do that in general, well, what you do is you project it in a basis. So if you go back to school and you go back to your university, one of the ways to model any function is what we call a Taylor series. You could say P of X is equal to A0 plus A1X, and you go on to ANXN. N is the degree of your polynomial, which goes back to the size of your model. And A0, A1, An is the basis, so it's your weights. Learning that is a question of minimizing a certain error compared with all the data. And you'll take all the data and you'll try to basically estimate all the different parameters. In general, well, when you minimize, it's optimization. When it's optimization, it means you do the derivative. If you do a derivative, it means you do a gradient. And in general, you use what we call a stochastic gradient or gradient descent algorithm, and you're able to learn all these things. Now, it turns out that if you decide to do a polynomial expansion of the PX, we don't necessarily have a nice architecture which is parallelizable to do that. It turns out that, of course, you need to think of an architecture where you can learn that distribution. It could be the RNN, we talked about it, it's not scalable, MLPFC, and it turns out that the transformer turns out to be the right one, okay? The second thing also, which is nice about learning basically in large language model, the system, is that it's a self-supervised problem. And so you don't need necessarily to basically label all the data, which turns out to be extremely complicated. Now, within the settings of people who are building these LLMs, you have different types of architecture. You have what we call an encoder, decoder only, things like T5, an autoregressive LM, decoder only, the GPT type, which is the mostly used at the moment as far as we are seeing, and the prefix LM, basically, which is being considered. And how it works? Well, in general, you have your text. You need to decompose your text into what we call the least representation. This is called a tokenizer. And in general, when we talk about data, we don't talk about gigabits of data, but we talk about gigabits of tokens, because depending on the language that you use, going to Arabic and whatever, things are a bit different. So you need to represent it through what we call a tokenizer. Then you do what we call an embedding. When you do your embedding, you go through this transformer architecture that we talked about, and then you go through what we call embedding plus softmax. You have basically your probabilities of your vocabulary size. You do your sampling, you predict the next word, and then you start again and you go on like that. Of course, it seems simple, but in general, of course, doing that on a very large architecture is what we call an engineering art, because basically if you want to do and build this system on 4,000 GPUs, you can imagine basically the problems that you have. The more GPUs on which you launch this kind of distributed manner, the more you have problems, the more cost comes up, and the more you need to care of a lot of issues that can happen. Now, of course, I talked about the classical architecture. Today, people are still moving forward, if you're interested to work on this topic, specifically of LLM, and building, of course, more and more, basically more powerful type of models. How they're doing? Well, they're still playing on the model size. They're still working on what we call the data size and trying to crash and get as much as the data they can. They're also working on extensions of the classical architecture by mixing models, or what we call experts. You have what we call mixture of models, which are appearing now, and mixture of experts. And then some people are also, of course, going on within this realm at looking at beyond GPT architecture, where they're using things like state space models. So you have to know that the field that I'm talking about now, although started a lot with this GPT type of architecture, now is moving into much more broader types of mixtures that people are doing. Now, a lot of the people, of course, can ask me, well, it seems that, you explained it in a certain way. It seems easy. Again, I told you it's a lot of engineering art. And in general, it's a very, very powerful engineering art on which you need to go. But one thing also that makes a big difference with the different players, and for which, of course, not everybody can go and play within the same realm, is, of course, the cost. I'm providing you here some numbers that are appearing here and there in different surveys. It tells you basically when you start building what we call foundational models, not the fine-tuned one on which you can build up a telecom GPT. In general, the money that you need to build is quite outrageous. Gemini is something that people are talking around $200 million. So it gives you a figure that not everybody can jump quite easily in building basically a super powerful type of model. And even if you decide to build a model and start basically serving it, playing with it. And I know some of my colleagues here have been trying to do research papers where they do prompting of these machines for optimization and whatever. And it turns out that the cost of the paper that they need to publish goes quite high because they need to spend a lot of instantaneous, a lot of basically inference on machines of different providers. And you have here basically the price that you're paying for what we call the input price or output price, basically for the inference price for different models. So we still have an issue today of bringing down, although the cost has been going down, but it's still costly. And the third one also, which I think is also important for many of you, is the fact that today, we have also an issue in terms of the energy spent to do these things. Here you have some numbers and predictions which are given. This was the same thing about the paper that I provided you at the beginning, explaining about how things, what situational awareness. And that paper, of course, tells you that by 2028, we're talking basically about 10 gigawatts of basically energy that is required to start, doing these kind of systems in terms of how we're building it, which is a small, medium U.S. state. And 2030, we're talking about 20% of U.S. electricity production. So what I mean by that is that there's going to be a lot of work that needs to be done to start, focusing on how to make more and more energy efficient type of models. And I think we are the best placed, by the way, in the telecommunication industry of doing that because we're running basically what we call mobile phones, we're running infrastructure. And on these things, of course, immediately you can't sell products if basically you need to recharge your phone every, I don't know when and then. And so there is, of course, an issue on how we're going to go forward, but I just wanted to mention that this is around that. And by the way, I've been advocating this quite recently, and the purpose of the ETI that we've been building is around that. Of course, I've been encouraging more and more of my fellows from academia to work on these problems. And of course, one of the reasons people are getting desperate in academia on this issue is exactly the fact that there's a cost of entry to go in this domain, which is not simple. There's a nice paper called Choose Your Weapon, Survival Strategies for Depressed AI Academics. I strongly encourage you to read it, which exactly expresses basically the situation in which academia is in the will of only focusing on theoretical problems, which I think is good, but should not be the only thing that academia should do, and not on practical problems because of the fact that they don't have the environment to work on the interesting problems on which basically they have been done. Because of that, you have to know that here in the UAE, we had a lot of discussions and we decided basically on the contrary that we need to support more and more academia to do their research, basically by providing them the environment. And environment here means compute. And we created what we call a Falcon Foundation. That Falcon Foundation has been supported by TII with an endowment of $300 million. And that foundation supports basically different research projects as long as they're open source, by the way, which basically, of course, work on enhancing whatever features that you can do in terms of research, either in verticals or on the core type of foundational models to go in the sense of course, solving this problem of that we're having between academia and industry, where basically we need to move forward. That was for 2023. And that was a big year in 2023, which we're seeing today also in this year to what we call smaller models. The second thing also, which happened in 2023, nearly at the same time, is what I call the 6G race. In June 2023, the I2WP 5G agreed on what we call the IMT 2030 frame. And that was very important because before 2023, there was still discussions about, if there's going to be one 6G standard, a couple of 6G standards, is it going to be some things that we're not going to have any kind of 6G? And that, of course, for me was the kickoff, basically, of what we call IMT 2030. By the way, some of you may not be very, I would say, knowledgeable about the telecom domain, but in general, if you're an engineer, you'll talk about IMT 2030 for 6G, IMT 2020 for 5G, and you go on like that, 6G, 5G, 4G, 3G are marketing terms. What I mean by that, you can put anything in it. Typically, the US, around 2010, I remember Sprint was claiming with a 3G CDMA network that they had 4G deployed just because they were kind of achieving those rates. So I think it's quite important also to distinguish that thing. Second thing also, which happened in 2023, was the end, where we had what we call the World Radio Congress, where more than 150 people, 50 countries gathered in Dubai with more than 1,500 delegations coming to discuss basically the spectrum allocations of 6G. And I think that was a very important day because it kickstarted basically the structure, and we came up also with what we want basically out of 6G. And instead of having what we call here the triangle, classical in 5G that people like you are familiar with, having more broadband, massive machine type communication, or LC, we came with something as an hexagonal where immersive communication, integrated AI and communication, hyper reliable and low latency communication, ubiquitous connectivity, massive communication, and integrated sensing and communications was at the heart of what we built. With also, as you can see, the KPIs on which we agreed on what we want to target as a 6G stand, going from the high data rate scenario of 1 terabyte wireless to things like positioning and forth in terms of discussions. And today, we have basically, I would say, 3 pillars which are trying to solve the basically KPIs that we're talking about. And I'll talk only about the third one because if it's of high interest of the work related to the talk I'm going here. The first call it, of course, is related to providing the broadband connectivity that is required in 6G. And here you have a list of candidate technologies that I'm seeing here and there being discussed, which each one has a potential. Of course, standardization will tell us what this will become. But here you have on the left, at least roughly, what are today the most advanced candidate technology to solve some of the KPIs I was talking about. And this goes from holographic MIMO, terabits coding, OEM, cell-free massive architecture, large intelligent surfaces, millimeter wave, LEOE satellite, beyond OFDM waveforms, ultra-massive access, NOMA and others, and time reversal. The second also, which is important, is basically a pillar, which also are technologies that fulfill some of the KPIs, is sensing and control. And this goes to joint sensing and communication waveforms, terahertz communication, wireless imaging, extreme RLC, age of information, and beyond sampling. And the third one, which also is at the heart of many of the KPIs that we're talking, and for which I'll spend time in relation to basically the topic that we've been discussing, is related to intelligence. And having, of course, this massive distributed intelligence, or even worse, or I would say broader, what we call here distributed GPT. And this goes to AI transceiver, to multi-agent generative AI, distributed GPT, how you do edge learning and edge generation, by the way. Mobile edge generation is becoming a big topic today. Semantic source code and semantic channel codes. And today, these telecom GPT pillars, we're seeing it in 3 fronts for that part. The first one is, of course, our industry trying, of course, to bring those models that can work efficiently with a lot of energy efficiency on all the devices that the telecommunication market can provide. This goes, of course, from laptop to basically phones to IoT to things which are, of course, a bit bigger than that. And of course, doing that is not easy. It's providing, of course, a new kind of opportunity for all the people working today in the telecom industry, because you have 2 ways of solving that problem. You can do it either at a post-processing level, meaning you take a model which exists and you start basically looking at how you do some kind of quantization of it so it can run within what we call the low precision that you have within your phone or your IoT, without losing, of course, a lot of performance. Second thing, of course, is also to go on the other side, is to do what we call pre-processing type of work. What I mean by that is that if you fix basically your architecture of your device with low precision, and typically where you assume, for example, that the weights of your model can only take values which are 0 and 1, you come back with something like binary neural networks. If you want to build binary neural networks and train a model by taking that, then of course you can't use a gradient descent because you cannot do a derivative in a discrete world. And so you need to rethink the problem of optimization, which is at the heart of learning, as a problem of combinatorial optimization. Quite surprisingly, I'm seeing a lot of my colleagues who are in the coding domain, people who have been doing Viterbi decoders, things like that, jumping now because there, of course, the doors are quite open for all the heuristics on how it becomes a decoding problem, on how you build basically a large language model with basically low precision, using, of course, all the ideas that people have been building out of decoding and coding. The second thing also, which is at the heart of the work that needs to be done, is starting to build what we call multimodality within our models. Before doing that, of course, you need to start doing what we call benchmarks and evaluations. Today, we don't have really a good basis like we have in English and others on how we evaluate and you can compete in basically building these models and saying, my model is better than yours because it was able to achieve blah, 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 blah. So you need to come up basically with some kind of leaderboard. And this is one of the work that we want to do also in this ETI, is helping, of course, the community by building a leaderboard. And on that leaderboard, of course, we can assess and evaluate models and we can rank them. And this, of course, is going to build a lot of good initiatives and how people are doing that. And so in general, when you build a model, you need, of course, to know what is the exams you're going to go. The same thing when you go to university. If people tell you you need basically to start, reading books and training yourself, well, you need to know, if I go to MIT and there's 20% of maths, then I will start concentrating with books which roughly, of course, reflect 20% of the work that I'm doing. And so for information, there's been a couple of benchmarks related to that. There's a paper where I've been working with colleagues on that related to Q&A benchmark and trying to find. But this is quite important. And more importantly, it's important because also the kind of things that we are using is also very specific to our domain. We're using what we call radio frequency signals. You want to do something like RFGPT, for example. You have, of course, sound. You have, of course, smell. You have, of course, basically video. All these are multimodalities that you can use to improve your system. And the third one, which I think is the most important from my point of view, is, of course, developing basically the infrastructure to provide these autonomous agents to interact. We still have no clue today if the cellular setting is the right basically kind of architecture in telecommunication to provide wireless autonomous agents to start interacting as if they are. I don't know if you know the story about cellular, but cellular came many years ago, already basically by paper of guys in Bell Labs at the time. But the fact that we came up with cellular is exactly that one of the big KPIs that we wanted is, of course, to be able to increase capacity. And what you can show is that if you decide not to structure your system with the cluster head in terms of transmission, then basically you will have a lot of interference generated and your system will go down. These are papers that have been published around ad hoc networks and showcasing that ad hoc networks, for example, do not scale exactly because of the interference generated. And so you need basically to partition your system when everybody wants to communicate, where everybody communicates within a certain region with a cluster head, and it's the cluster head which communicates to another cluster head and give. And here we have the same thing when we're talking about autonomous J agents, in which one of the things is about inference and learning. The question arises about what is the kind of scaled architecture that need to be built, and this, of course, provides you degrees for us in the building the next generation system of what we're doing. Of course, the movement is not waiting for 6G to be built. Let's face it, we're already seeing people now moving within the actual, I would say, standards have built to start building, of course, these agents in a wireless manner. In the last Mobile World Congress, there have been an announcement by already Dutch Telecom, looking, of course, at what we call AI phone. And the AI phone was basically a phone which basically has no apps with these kind of agents that you want to build in that. And I think this is going to be going more and more. But again, as I explained at the beginning, there's no reason why you cannot build a technology within an actual standard. The question that you always have to ask yourself is, when I start, of course, scaling, moving, I need to understand what limits me now so I can change it, tweak it to make a standard which fulfills all the degrees that you can have on a theoretical or non-conventional with, I would say, firm structured system. Another also thing that is part of the talk that I'm giving here today is, of course, that we decided also to be able to structure basically our community to kick off something called a large generative AI model in telecom, GenAINet, where we're having different partners coming from academia and industry discussing already basically the potential of these systems as basically the next generation building blocks of the telecommunications. So I strongly encourage you to follow also the work which is being done within our basically ETI to learn more about what we're doing and the work that we're doing. Now, a couple of examples just to give you, and these are examples that you can find in the papers that I have been mentioned. There's a couple of other papers. I cannot spend all the different things that you can do, but roughly if you want to separate the system, you have two things. You have what I call here LLM for telecom and telecom for LLM. LLM for telecom is exactly the will, and we're seeing a lot of people now, of building a large language model, fine-tuned on general, basically by taking an open source one and then adding data or private data, which are the physical layer, the network layer, whatever, and then basically to improve the classical things that you need to do. You can do LLM for slicing. You can do basically LLM for B management. You can do basically LLM for modulation, and you can improve basically different features. You can do that, of course, as again, not necessarily on a 6G scenario. You can do it for any kind of system that you want by taking all the different features that you are measuring and the data to be able to improve. The second thing, which I think has much more potential, is of course how we, as basically a telecom infrastructure, we can improve the way that, of course, generative AI is being built, and how, of course, we let basically this collective intelligence to be made. And for the protocols, the languages, the interfaces, and this is where the doors are open for standardization, because standardization will never, of course, standardize AI, but you standardize what we call the interfaces, how these things talk. And we know that the future is exactly about basically an agent talking to another agent, and you need to interface how these systems are going to be done, and also what is the kind of language that they need to interact with, what would be this universal type of language, and with the features that it has to be able to make this happen in a certain way. And just to give you a couple of examples, which have been done also with my colleagues, the first thing that we've been working for the case of LLM for telecom, not the other, is looking at the capability of using basically large language model to do what we call 3D reconstruction. And basically what the idea is, of course, that with the environment and the data that you have, you could provide what is the most probable 3D environment corresponding to the measured radio signals that you have been doing. And so this is the kind of work that we've been doing quite recently, looking at what we call RF visual language models. And this is quite important. Of course, it's not so surprising that you could do. The people who are working in the radar industry have been doing that in terms of identifying objects. And the idea is, of course, that you want to use, of course, the powerfulness of the system from going from an environment image and channel measurements. These things can be done in a real domain, or of course, we'll talk about it, they can be done in domain, meaning that you generate this through simulator and all the things related to synthetic data, and you start building your system to have these things. And the work that we've been showcasing has been showcasing some good numbers on how you can reconstruct on the vice versa from the image to the channel position and vice versa to do this kind of RF GPT framework that we're talking about here. Second thing, as an example, for the time I have, is of course the case of building basically, as I told you, kind of infrastructure that you want to do. I didn't talk about a case, of course, of fine-tuning models with 3GPP documents, things like that. I think we'll be seeing more and more of these things being done in the short run. You'll see more and more what we call extremely powerful fine-tuned models, which are serving for the operation and management in companies and stuff like that. And I think this is something that, of course, you can go. Here, what I'm talking is more about the fact that the LLMs will be distributed either at the mobile phone base station, and you want to build some kind of architecture and system that they can do. And for that, we released a paper where we're looking at how when LLMs are at different mobile phones and at the base station, when you want to basically optimize the system by giving on a language form, a target of reduction of energy efficiency to the system, setting and telling to the system, I want my system to reduce the consumption power by 0.85 watt, for example, that's the example we gave, while keeping the transmission rate, and letting the system trying to distributively find a solution through iteration and optimize. And so this is the example we've been showing on how these systems are extremely powerful also in terms of giving a prompt, and then you get a system which solves that prompt in terms of complex problems that you have with these agents on which you fix the targets. And here, as you can see, we've been building that and looking at the number of iterations around that and in terms of how you converge towards basically the solution we've been going. By the way, I talked about LLM as compressors. Of course, LLM are also what we call optimizers, and this is a very good example on how telecom AI agents can be used as optimizer. Okay, I think I finished my talk right now and gave you a bit of an overview. I went a bit higher than the time, but I'm happy to answer any questions, give you a large overview about all the things which are happening within our domain.
Yeah, thank you, Professor, for the very, very insightful talk. Now we are running out of time, but maybe we can accommodate 1 or 2 questions. So any questions from the audience, you can either type your question in the chat window or you can raise your hand.
People are afraid of questions.
Yeah, maybe I can while people are thinking about question, maybe I can ask a question, Professor Debbah. You talk about 6G, mobile for intelligence in 6G, right? And we know that 6G is very 3GPP is going to start 6G standardization very soon. So we have very short window. So how do we educate the industry who is in charge of standardization, right? How do we educate industry to build 6G ready for intelligence?
So that's a very good question. I think there's 2 things that matters here. The first one is so for everybody, I mean, what Lin is saying, I'm just trying to share. Yeah, I'm just trying to share my slide. What Lin is saying is, first of all, that the time that we have is quite short. When you look at 2030, you see here, you have basically a work which is being done where the study group will start already very soon, meaning in 1 year or so. And then basically from that, you have specs. So the time is very close because once the spec is done, you're a bit out. And so you're totally right. The first thing in general that you need to do is, of course, why you do it. And I think what we've been seeing is a reluctance of basically mobile operators to deploy 5G because it costs you to deploy, but you don't know how to make money. And I think the first education we need to do, and we have a bit of time now, is to take this opportunity to start looking at what are the new business opportunities that we can leverage from basically the fact that we're deploying this infrastructure which has agents in it, and how we can build up marketplaces. This is up to you and things like that. The education has to be first done on to push people to accept this mobile intelligence. You need to tell them how you make money out of mobile for intelligence. Otherwise, we'll get the same thing as 6G, as 5G. People will be reluctant to deploy it because they say, I want to make first money of my 5G. Why are you talking about 6G? Here, what I'm saying is that the last 4G and 5G, we've been losing money because it's classically the other type of companies which are making money because they're using the dumb pipes. And here what I'm saying is, I think the fact that we are a distributed computing platform on which we can leverage the fact that we can guarantee an end-to-end latency quite rapidly so things can be built quite fast is something on which we can leverage because people will run whatever they do on our infrastructure, basically. And I think this is quite good because I'm not saying that I don't believe in the cloud, but I strongly believe in the fact that things being closer and this agent kind of system is going to be done. That's the first thing. Second, of course, is the support that we need to kickstart providing to the different players. Today, many of my colleagues don't have GPUs to start working on these things. They can't. They can't work. Especially my colleagues in academia, and especially my colleagues in academia in countries which, as you know, cannot afford that. And I think this is also a big step because innovation will come from all the places of the world. And we need also to find, like we did for the foundation, ways. And you, for example, I know your company is also doing a bit of initiatives of basically supporting different institutions around the world. We need to support more to get the best and educate the whole basic academic industry to start working on these problems and accelerating the pace of innovation.
Yeah, that's very good to hear. We need to really see business opportunities in order to make that happen. So we see a lot of questions coming up from the audience, Professor. So maybe the first, Yan Sha, you may unmute yourself and ask directly.
Yeah, thanks for the nice presentation. So, I have a question related to the, reliability of the large language models. As you know, like some of the resource management and control, we can also use the conventional reinforcement learning or other approach, conventional approach. So how can we guarantee that the output generated by large language models can be reliable and trustworthy, especially when it relate to more, sensitive applications?
So that's a good question, which has not been completely solved. So now there are a couple of papers which are really reducing basically the hallucination, or reducing also basically the kind of errors that you're doing by using what we call a game theoretic setting, where the system basically interact between them many times. And so rechecking. So I think there are avenues to do it. We need to solve that if we want to have a robust type of solution. But I think this is the way to go from my point of view. We need to go because you have a feature. One of the things about these systems, which also are very nice, is that usually the way we have been working is developing a model, developing an autoencoder, for example, if I take this case, for optimizing the various things that we knew what we needed to solve. Many of the cases, you don't know what you need to solve. And these LLMs in general are able to cope with new cases that you have not taken into account at the beginning.
Thank you.
Yeah.
All right. So next in the queue, David Jia. So would you like to unmute yourself, ask the question? So you're still on mute, David.
You're still mute. Jia, you're still mute. You have your hand raised, but you're mute. Okay, I know.
Yes, sorry. Thank you, Professor. So I'm David Jia from Telecommunications. I have a question.
Jia, your voice so weak, I cannot hear you.
Yeah.
Could you please increase your volume?
Can you hear me now?
Yeah, a bit.
Yeah. So I had a question. Do you have examples of industrial applications of LLM for telecom? Because each time I see an example of model of LLM for telecom, it solves a kind of allocation. But I can't see a lot of application requiring a textual data. So I feel like these proposed models can be replaced by simpler models without textual data. So I don't see a lot of applications of LLM for telecom.
So one of the things that people are highly interested that we're seeing is so there's two things. I've been talking more around basically the, I would say, technology part of the infrastructure. However, one of the first application is, of course, all these operation and management, and by building a fine-tuned telecom model for the telecom industry. What I mean is that you have an engineer which goes in the field, okay? And there's a model, by the way, TII is building one of them, where basically you fine tune, and then when you go on the field, you say, okay, I have a red plug, and I have a white plug, and I need to change that. What should I do as a feature? And he tells you step by step, push this, take this, put it down, things like that. So in terms of people who are working in the field, basically in terms of operation, things like that, these kinds of voice models, basically where you can talk to the model and tell them, look, help me now what I should change because I have this blocking effect or whatever, are things that people are interested in. We're seeing that a lot of interest for basically fine-tuned models, which are very relevant based, of course, on the legacy of data that an operator has because of all the knowledge that the engineers had. And basically when you go in the field, you can, of course, fix, change, things like that. Or even for you, you have a Wi-Fi router, you want to say, how can I configure my Wi-Fi router with this? You get a very decent response, things like that. Second, of course, is also all the part generating to code. You want to generate some kind of code, with the Gnode B, whatever. You can type with the text, you get it. But that I would say is the most classical thing that everybody's doing in its own vertical. Meaning you'll do it in a vertical medicine, they will have these things about these questions, and you can do. But this for sure is something on the operation and management case that we're seeing, which is quite nicely. On the top, of course, service level, highly interested. But these are more like basically classical routine calls, things like that, how to treat them, things like that. When we're going on the physical layer, it's only started now. And the examples that I gave you is mostly about, doing 3D imaging, using basically multimodal models, for example. Trying basically, of course, to improve some kind of AI-based massive MIMO beamforming, which was done with the autoencoder, and now using a more generic type of large language model. For this, it's only starting now.
Kind of GPT expert, as you say in the first case, to help the operation.
Yeah. It's a GPT expert fine-tuned on your own data and legacy data and for which you go. And also even for standardization, you want to get 3GPP documents, things like that. Today, the search for people who do standardization, and I think Lean can talk about it, it's crazy the number of documents. You don't want to spend time looking at all documents, just want to ask question, okay, in which release this has been done, blah, 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 and you get all the information and you say which features was done quite recently, and it gets you all the response. So training all these things for all these people who are doing standardization, getting these documents, the features, things like that, you have a 3GPT telecom expert that you can build, yes.
I see. Thank you for your answer. Very interesting.
Yeah, thank you, David, for the question. We have also two quick questions in the chat. The first question is from Li Xia, but unfortunately, Li Xia has left already. But anyway, the question is, what are we seeing large action model potentials in the context real world use cases?
So what are we seeing large action models potentials in the context real world use cases? Well, the LAM is today the next step after the LLM. The big question, as you know, is that LLM gives. So today, what we're seeing is people are saying, "Oh, tell me what is the best pizza in Abu Dhabi." But in fact, your goal was not to know what is the best pizza in Abu Dhabi. You wanted to say something more like, I want the best pizza of Abu Dhabi in my house in 5 minutes. And the question is how you go from an LLM, which provides you the answer of the best pizza, to an action where you will get it. And of course, the kind of potential is how you translate basically these information into an actionable system, which provides you the solution. And today what we're seeing, of course, the kind of real world use cases are exactly that. You're asking not a question about what is the best pizza in Abu Dhabi, but I want the best pizza in Abu Dhabi in my house in 5 minutes. This, of course, will generate a whole pipeline in terms of system of communication, where it will go from a mobile phone, your agent will go start negotiating also maybe the price, come back, and you need basically to go all through this feature, and maybe also a marketplace where these guys will start interacting. This I'm not working on, but we're seeing this potential.
All right, thank you. Maybe one last question in the chat from Akron. Some recent researchers advocate that LLM would be energy efficient for telecom, or maybe Akron would not be energy efficient, and therefore small language models and domain-specific LLM. So the question is, do you think the small language model will be so efficient to replace LLM in telecom?
So let's say, first of all, I think we don't have a choice. We need basically to come up because the system, I gave you those numbers that people are talking about. All these guys which are building LLMs, they're talking about now powering stuff with nuclear plants, whatever. It never ends. And I think there's no choice for us. And if we want to continue, we need to build basically systems which are very energy efficient. Of course, systems which are smaller turned out to be, of course, more energy efficient, and at the same time, of course, more costly to infer. So that, of course, is a good step to go for that. Second step is also to go outside the thought of how we're building this system of GPT and going on beyond GPT architecture to look at how we can build them. And so for that, of course, one way to do it also is to look at also specific hardware architecture which you can build, because there's the fact that you build the LLM or SLM, but then also on which you run them. I'm talking here to Lean, which I know is proud of his GPUs, but we're seeing, of course, people who are designing specific things like LPUs, large processing units, which are very specific to doing a task like inference. So there are a couple of companies which are now providing that. It's not only, by the way, only on the energy efficient setting, it's also on the number of tokens. You remember I talked about mobile edge generation. In telecom, mobile edge generation, you're not going to wait 1 hour before you get the result. It has to be extremely quick. So the number of tokens per second which are running has to be fast. And of course, we're seeing on that inference part, at least not on the training, at least some people are now also looking at very specific hardware architecture. I strongly believe that we will start having very specific hardware architecture which are built on the phone, on the IoT to run those systems. Yes. But maybe Lean will tell you that he'll still run his GPUs.
Yeah, you still need GPU, lots of GPU. All right. I think we are running a bit late. Thank you everyone who joined us for today's webinar. And Professor Debbah, thank you for sharing your insights and expertise. So
thank you very much.
Yeah. So if any of you have additional questions or would like to connect with ComStar ETI on large Gen AI models in telecom, please reach out to us. And thank you for your time and have a wonderful rest of your day. Bye-bye.
Thank you very much.